Hi, this is the first video for chapter 14 on properties of gases. So gases have some general characteristics, so we're going to go over that first, and then we're going to move into the different equations that we use to calculate different aspects of gases. So this is chapter 14.1 in your textbooks, or chapter 14 in your textbooks, and we're beginning with part 1, which is just kind of some basic concepts of gases. So properties of solids versus liquids versus gases, and we talked about this way in the beginning of the year. We said solids have a very fixed structure. The shape and the volume is very fixed. It doesn't really change very much because the particles themselves are packed very closely together. Liquids are pretty close together. There's just enough space in between those molecules that they can actually slide past each other. So there's just a little bit of room in between here, so that they can kind of slide around and slide past each other. But they're really not very compressible. You can't take a sample of liquid and squish it into a smaller container very easily. That would take a tremendous amount of pressure, and you wouldn't be able to compress it very much. So we really say that liquids can maintain the same volume, but they can change the shape to be whatever the shape of their container is. Gases, however, are mostly empty space, so they behave very differently than solids and liquids. Gases can be compressed. They have something called compressibility, so it means that you can take a sample of gas and squish it into a smaller sized container. That causes an increase in the pressure of the gas, but it can be pressurized. So you think of even, you can buy compressed CO2 canisters for paintballing or other applications. They actually use compressed CO2 to carbonate fountain drinks and so forth. So we know, it's pretty commonly, there's some pretty common uses for compressed gas. So in this chapter, we're actually going to learn how to calculate different aspects of gas. So the factors that actually affect gas pressure are temperature, volume, and the number of particles or the number of moles. Remember that moles is a measure of particles. And we talked earlier in the year about, moles as number of particles. One mole of anything is 6.02 times 10 to the 23rd particles, and 1 mole at standard temperature and pressure always occupies 22.4 liters, and that's true of any and all gases. So we're going to talk about calculations between pressure, volume, temperature, number of moles as we go through this. A couple of things, one thing I do want to mention is kinetic molecular theory, because that pertains not just to gases but other things as well. Kinetic molecular theory really just says that, and this says gases, and this was taken from your book, but really all things consist of small particles that have a certain amount of motion. Certainly gases have a lot more motion. Remember, solid particles are very fixed in place. But all substances have energy. When that energy level increases, there's a certain amount of expansion. As temperatures decrease, there's, things contract. And so I always say people who build bridges, remember, I'm sure I mentioned earlier, need to understand that, so they make joints that can expand and contract with changing temperature conditions. So the first gas law that I want to talk about is something called Boyle's law. So Boyle's law really says for a given mass of gas at a constant temperature, so we're not changing temperature, the volume of the gas varies inversely with pressure. So inversely means opposite. That means if we increase the pressure, the volume is going to decrease. And that makes sense because we could take a balloon and if we compressed hard enough, we could squish it into a container that was smaller than that original balloon. If we did that, it would be under pressure. So that's an inverse or opposite relation. So it's inversely related. As pressure decreases, volume increases. So if I reduce that pressure on the balloon would expand to its size that it was before we applied the pressure. So that kind of makes sense. Boyle's law has a very specific equation, P1 times V1. So P1 stands for pressure number 1, and V1 is volume number 1, is equal to P2 times volume 2. So what this really says is the original pressure and volume, pressure times volume, is equal to the final pressure times volume. So if I take that balloon and I multiply pressure times volume and I get a value, if I compress that balloon, the volume is going to be smaller, but the pressure is going to be larger, but it's in a relationship with each other, so that, for example, if the volume, if I compress it to half its volume, then that pressure is going to increase proportionately, so that if I multiply them together, P2 V2 is going to be equal to the same value as P1 times V1, if that makes sense, and I hope it does. So let's do a quick little calculation here. So if we have the equation and we have, I've written, over here the values of, P1, V1, P2, V2, and so forth. So in the equation, if P1 is 103 kilopascals, and kilopascals is really commonly used to express pressure, as is atmospheres, which I have at the, atmospheres, and also millimeters of mercury. So I just have at the top here so 1 atmosphere is equal to 760 millimeters of mercury. 1 atmosphere is also equal to 101.3 kilopascals, or also 760, sometimes instead of millimeters mercury, you might say torr, 760 torr is also equal to 1 atmosphere. So just remember what you started with, okay? So we're using kilopascals, so we just need to be consistent all the way through. So 103 kilopascals is pressure 1, volume 1 is 30 liters, and pressure 2 is 25 kilopascals, and we are trying to solve volume 2. So we want to get volume 2 by itself. If you remember simple algebraic manipulation, we really just need to divide both sides by 25 to get that volume 2 by itself. So remember, you're going to multiply these two things and then divide it by 25. If I perform that calculation out, I end up with 123.6 liters. And I am going to pause this while I do the calculations. It takes a long time to write them, and I'm trying to get as much as I can into a 15-minute video here. So, and then always evaluate your answer. Does that make sense? Remember that temperature and pressure are inversely proportional. So if pressure 1 was 123 or 103 kilopascals, pressure 2 is much lower, so my volume went down, or my pressure went down, sorry, my volume should increase, and it did. So that seems very reasonable. So that's just a quick example of Boyle's law. Charles' law then deals with the relationship between temperature and volume. So Charles' law says the volume of a fixed mass of a gas is directly proportional, so not inversely proportional, but actually proportional to its Kelvin temperature. Oops, remember we talked about Kelvin temperature way back in the beginning of the year. So when we're dealing with these gas laws, we actually have to use Kelvin temperature and not Celsius. So we'll have to perhaps be doing some converting back and forth. So the volume of a fixed mass of a gas is directly proportional to its Kelvin temperature if the pressure is kept constant. So just like when we talked about Boyle's law, we didn't take temperature into account because we were saying if the temperature is kept constant. So the thing that's kept constant, we're not going to worry about in these equations. So in this one, we're not going to worry about pressure. This equation is used only to calculate between different volumes and temperatures. So the ratio of volume 1 to temperature 1, so volume 1 divided by temperature 1 is equal to the ratio of volume 2 divided by temperature 2. And I apologize for that writing. I had a typo on here, so I had to write over it. And it's ugly. But so if I'm given volume 1 to be 4 liters, see where my volume 1 is going to go? And my temperature 1 is 24 degrees Celsius. Oops, it's in Celsius. So remember I said it has to be in Kelvin. So I'm going to convert it to Kelvin. Technically the difference is this, the value is up here. You're going to take the Celsius degree and add 273.15. You can drop the 1.5. Nobody really is going to care about that tiny little amount. So I just take my Celsius temperature and I just add 273. Super simple. So 24 degrees Celsius is 297 degrees Kelvin. My temperature 2 is given as 58 degrees Celsius. Again, we need to convert that to Kelvin. We add 273. And then what I'm solving for is my volume 2. So how am I going to get volume 2 by itself? Well, because the 331 Kelvin is on the bottom, you actually have to multiply both sides by 331 in order to solve this. If I do that with my handy dandy calculator, I actually end up with 4.46 liters. And then does that seem reasonable? Does that seem like a reasonable answer based on what I started with? I really didn't change my temperature very much, but my temperature did go up from 297 Kelvin to 331 Kelvin. So my volume should increase a little bit, and yeah, it did. It looks perfect. The third gas law is called Gay-Lussac's gas law. This looks at the relationship between pressure and temperature. So it doesn't deal with volume at all. So the relationship between pressure and temperature, it just says the pressure of a gas is directly proportional to the Kelvin temperature. And again, we have to say that the volume has to remain constant because there's no place for volume in this equation. So the volume has to remain constant for that to be true. If the temperature is doubled, the pressure also doubles because we said it's proportional, not inversely proportional. So if I'm given some values of pressure 1 divided by temperature 1 is equal to pressure 2 divided by temperature 2. So I have set up an equation, and every year when I teach this, students say things like, well, we learned the ball, like this is the bat, like right here, and then you hit the ball, and I'm sorry, I don't know that kind of math. If that's a way to help you remember how to do this, you're certainly welcome to do that. The way I do this is multiply it by the inverse. Obviously, I want to get T2 by itself, and that's what I'm solving for, but I don't want that to be on the bottom. So you multiply by the inverse. If I multiply by the inverse, it means I take the 101.3 that's on the left side of the equation over 297, and I flip it. I'm going to multiply both sides by that inverse. If I do that, I actually end up with 437, I think that's my number, 437.8